This week, we're talking about categorical data and chi-square tests, and we'll go into what are called more advanced techniques called CART models or classification and regression tree models and logistic regression. So I haven't talked about this much, but this is the same diagram that you'll find in the JUMP program, showing you that you can have either a categorical or a continuous y-axis, and you can have either a categorical or a continuous x-axis. Now, for the most part, so far, we've only talked about continuous y's, and we've done t-tests. And so you've been in kind of the top left-hand box, and we will cover ANOVA eventually and regression correlation. But for this week, we're going down into the bottom box, where we're dealing with categorical y variables. And we're going to talk about situations where you can have either a categorical x, like you've been used to, or a continuous x, and that would be a logistic regression model. So bear with me. This is where we're headed this week. So categorical variables can be a variety of things. They can be things like color, red, green, blue. They could be sex, male, female, intersex. They could be species, so different types of species. Each species name is a category. Habitat type, so are you comparing lakes and streams, or 3 different lakes, different forest types? Something is either alive or dead, that's a good category. So mortality data would be categorical data. Presence, absence, sometimes we deal with communities in terms of presence and absence. And so we're gonna use what are called chi-square tests this week. Chi-square is a new distribution. So we've used the t distribution so far, and this time we're gonna be using the chi-square distribution. And you use these kinds of tests when your dependent variable, your y variable, is categorical. Or you can use these types of tests when you have some observed value in nature that you want to compare to some expected value. And so you also can use them in a third way, which is when you want to test whether 2 things are associated with one another. So maybe the presence or absence of one species is that associated with the presence or absence of another species. So our 2 categorical variables dependent on one another. So in the case of observed versus expected, some examples might be things like, is my milk really 2%? So you can test the actual fat content of your milk and compare it to a 2% expectation. Do leaf mixtures decompose at rates expected based on each species decomposition rate in isolation? So this is one example that I've used chi-square tests for in my research. Hardy-Weinberg equilibrium in genetics. So do populations behave such that they're in Hardy-Weinberg equilibrium? Do they behave as expected based on that model? And Mendelian genetics, so ratios that we might expect based on the genetics of a situation, are the patterns that we observe actually matching those expectations? And then habitat preferences. So you can use this when you're testing to see whether an organism is preferring a specific habitat more so than that habitat is available to them. So for example, we'll start with a habitat preference example, and these are all similar to the examples you're going to see in the lab. So I'm just going to walk you through how they work. The first one is, do salmon prefer certain habitats in streams? Well, let's say a stream is composed of 55% sandy bottom, 25% gravelly bottom, and 20% silty bottoms. If the salmon don't prefer any of these habitats, when you go to a stream, you'd expect to find 55% of the salmon on sand, 25% of the salmon on gravel, and 20% on silt, right? They don't show any preference for the habitat. But if you go to the stream and you see salmon preferentially choosing specific habitat types, then you could say that the salmon statistically prefer a certain habitat. So you might know something about salmon. You might think that they prefer one of these habitat types over another. So what you would do is you'd go out to the stream and you'd survey salmon, and you would basically just note where every salmon was present and what kind of habitat type it was found in. And you would record those data, and then you could enter them in a table, and then you could enter them into JUMP. Or you could tabulate them, you could count them up. And so here's an example of the data on the left, and then this would be what you would if you counted them up. We observed 8 salmon in the sandy habitats, 18 in the gravelly habitats, and 4 in the silty habitats. Now, what you need to run a chi-square test, what's really cool about them is you can do them by hand on a calculator or in Excel, and you can do them in the field, which is really fun. So what you do is you add up the total. And so we observed a total of 30 fish. And we have 3 different groups here. We have sand, gravel, and silt. And so group numbers usually represented by A. And so our degrees of freedom are A minus 1. So we have 3 groups. Our degrees of freedom would be 3 minus 1, which is 2 degrees of freedom. Then what we would do would we would calculate how many fish we'd expect. So for 30 fish, if we were to expect no preference, we would expect 55% of the 30 to be in the sand, 25% of 30 to be in the gravel, and 20% of 30 to be in the silt. Okay, so we would calculate that, those expected values, and then we'd compare our observed values to our expected values. And we use a specific equation to calculate the chi-square value. And so if we just looked at the data, we see very few fish in the sand, although we'd expect 16 and a half. We see 18 fish in the gravel, but we'd only expect 7 and a half. And we see 4 fish on silt, and we'd expect 6, so that's pretty close. Okay, but it looks to me like we might have a pattern where fish prefer gravel habitat, and they are there at higher than expected numbers. But we need to run a chi-square test before we have confidence in our answer. So here's the chi-squared equation. Chi-square, not chi, but chi-square is denoted by a big capital letter X or chi and squared. And then that equals the sum of every value from I equals 1 to n, so across your whole sample size, of every observed value minus the expected value squared divided by the expected value. And so we can see how this would work. We observed 8 fish in the sand, but we expected 16 and a half. We take 8 minus 16 squared, divide by 16, and we get 4.38. We do that for each group. So we observed 18 in the gravel, but we only expected 7 and a half. We subtract those 2 numbers, square them, and divide by 7 and a half. In the silt, we observed 4, we expected 6. 4 minus 6 squared divided by 6 is 0.67. Then we sum those 3 values up, and we get 19.75. So now we have our chi-square value, but how significant does it have to be to show that salmon prefer specific habitat? We would have to go to a table of chi-square values, knowing our degrees of freedom are 2, okay? And so we go to a table, well, here, I'll show you distribution of chi-square values first. So here's what chi-square looks like as degrees of freedom grow from 1, 5 to 9. So you can see it's a skewed distribution. It's not a normal distribution. So that's first, but these curves don't really help us very much. Easier would be to go, although I guess going back here, 19.75, you can see that's a pretty big chi-square number because this only shows you 20 and then going on to infinity. Okay, so if we go to a table of chi-square and we look for 2 degrees of freedom over here in this column, this is the degrees of freedom column, so we find 2. When we go across until P is 0.05, we see that the chi-square value, the critical chi-square value, is 5.991. So as long as our chi-square value is larger than 5.991, we can reject the null hypothesis. Okay? And in fact, if we keep on moving along here over to the right, we can see that our value of chi-square is actually larger than this value, 10.5, which is at a P of 0.005. So we could say, and this is how I'd interpret these data, salmon show a significant preference for specific habitat types in streams. A chi-square with 2 degrees of freedom equals 19.75, and the P is less than 0.005, right? And I got that from the table. In fact, they appear to prefer gravel habitats. So that's one way we can use chi-square tests. We're going to take a 10-minute break, and we're going to come back and learn about Mendel's P's.